So today I want to look at trying to take a concept in mathematics that's that you know how to deal with analytically, and just try to figure out how to map it onto the computer and figure out how to implement all the things you want to do to these to this object. So we already saw that polynomials show up often when you want to have approximate solutions to things. For example, the root finding assumes that the function is linear. Right? Linear functions are polynomials. Integral assumes the function is constant or linear or quadratic. And you could generalize this. So the reason polynomials they show up often is because they are one of the simplest kind of functions, and they approximate many functions relatively well. So we can ask the question, well, how do we tell the computer about polynomials? How do we figure out a way to map this idea onto the hardware? So here's a polynomial, a times x squared plus b times x plus c. Right, that's a polynomial. We can write it in any order, right? We can write it like this. If we want to. Doesn't actually change anything. And what changes when you look at two different polynomials? Will be you'll get different numbers in front of your variables. So b1 x plus c1. Right, these so-called coefficients are the things that you have to remember. So when you deal with polynomials, you might not have noticed this, but when you add polynomials, multiply polynomials, when you derive polynomials, you don't actually play around with the variables. It's only about the coefficients. Alright, so let's try to just write them in this very minimalist way. Right? Let's boil down polynomials to the smallest representation, which is easily understood. You know, there might be even smaller representations that are more complicated to understand, but this one is pretty straightforward. So we're going to make a new type for polynomials. Polynomials are going to be a new type. And we'll pack a few things together. First pack a pointer to a double precision address called coefs for coefficients. Then we'll have an int int will be is going to be the length n is going to be the length of the array of coefficients. Polynomial. To show you what I mean, I'm going to construct the polynomial as described here, which corresponds to the polynomial 5x squared plus 6x plus 7. is equal to, if you've never seen this, not sure if I showed that last time, but so this line simply goes into memory and reserves a chunk of memory, of contiguous memory, which has n times, in this case, 8 bytes. So 3 times 8, which is 24. It's got 24 bytes of consecutive memory. And I allocated this memory. So malloc returns a pointer to memory, which is a void pointer, and you have to change the type so that you know that you're pointing to a double precision number by casting, like changing the type like this. So you want a double pointer to double. That's the first thing in your polynomial, and p dot n equals n. I could have put m here and I would have put m there, but I would still have n here because this n is a name that belongs to poly. All polys have this name, whereas this is just an int. But why complicate things? Okay, and actually, so p dot coefs, and you can use this notation. So the first thing is going to be 7 p dot coefs 6 p dot coefs 5. So as you saw, I wrote it backwards so that the constant term is the first in the array of coefficients. Okay, and maybe I can write a print function. So void, meaning it